So this is a session where we've got two speakers from the University of Melbourne. The first is Peter Forrester, and as you can see, he'll speak on reminiscences relating to Rodney's work in 83 and 84. Thanks, Peter.
Yeah, thanks very much, Murray. So to everybody, indeed, as Murray commented yesterday, tying it back to 2025 is hardly as anyone would have wanted. On the other hand, as Murray also said, it does provide an opportunity to pay our respects to Rodney generally and to highlight his academic legacy. So yesterday we got things off to quite a start with Murray personally providing that respect, and then we heard from Vladimir highlighting Rodney's academic work. Next, Paul spoke and said we'll change gears and we'll go to the scientific side of the conference. Well, actually, my talk is really only an asterisk to both Murray's and Vladimir's talk, in the sense, footnote, let's say. I will be returning, as Murray said in introduction, to the years 1983 and 84, and saying a little bit about how I also became Rodney's student. So that'll be my first part, a few slides on that. Then I'll move on to the topics of 1983-84, the two topics, 8-vertex solid-on-solid model that we heard from Vladimir yesterday's amylogical model. And I'll conclude with some comments of mine about how I look at Baxter's legacy in the broader context, or firstly, the more specific context of exact solutions in statistical mechanics in Australia, but then the broader context of integrable systems and solvable models. All right, so let me go one slide at a time. How did I become Rodney's student? Well, it goes back to the years 1980 to 1982. And we already had a number of people in, I was an undergraduate student at the University of Melbourne. We already had a number of people who generally worked in the area of condensed matter physics or statistical mechanics. So just let me recall some names here. In the physics department, Ken Hines and Norm Frankel. We also had Bruce McCullough. Bruce wasn't known as a person working in condensed matter specifically. He's very general orientated as far as his research went in theoretical physics. And significantly, Bruce McCullough was my third year statistical mechanics lecturer. And I really took some liking to that topic. I think in third year, quantum mechanics and statistical mechanics were definitely my preferred courses in the physics department. I took courses in the maths department. In the maths department, I always liked math methods type courses. So over in the maths department was Colin Thompson. Colin was mentioned yesterday by Murray, saying, telling us that Colin shared an office with Rodney in his MIT days. Colin had already had a book, a little small book called Mathematical Statistical Mechanics. He sometimes used that in courses, although I didn't actually get to hear his course in fourth year. Instead, and also by that stage, Colin was actually researching models of chaos, which is quite popular in the early 80s. Instead, in fourth year, I had as statistical mechanics lecturer, Ed Smith, and Ed's topic was fluids, and particularly fluids with systems with long-range forces. And at the end of third year, got partnered up with supervisors for fourth year. And in fact, in fourth year, I did a joint physics and mathematics honours year. And it was sort of guaranteed from the word go of coming both top and bottom of the class, because actually I was the only student enrolled in that. And I'll sort of come to that in a moment about the the atmosphere, if you like, in the early 1980s as far as future of higher studies went in Australia. It will come up. And also perhaps answer Murray's question of why Rodney was somewhat reticent to think of having any more than one student. So as I mentioned, at the end of 1980, I was given an honours project to start in 1981. And I used that sort of summer break to go over this topic of ladder sums. Ed Smith gave me a review of Larry Glasser, who's also associated with Rodney to some extent in those MIT days, I believe. And I worked through that over the summer break, and that's sort of significant because it introduced me to the very first time to these Jacobi theta functions, which I took quite a liking to. The main problem was that the ladder sums that one encounters in electrostatic systems perhaps for simulations of ionic fluids are very slowly convergent, and one wants methods to make them rapidly convergent. So it required, as it turned out, some transformations that come up in like Poisson summation, but in higher dimensions on lattices. The side of that is there was, as I said, Jacobi theta functions appeared, and I took some interest in identities that really had no sensitivity to identity before this summer of the end of 1980, start of 1981. And one of the ones I came across in the context of reading that review was this here, an identity which involves a cube of a single sum equaling on the right hand side, a one-dimensional sum. And I realized from the progression of studying that review on ladder sums that actually had some implication in the actual applied topic I was studying, which was the potentials in these electrostatic crystals.
Peter, just a moment, it's not scrolling. We're still on the first page.
Oh, really?
Yeah.
Okay, bad luck. So is that sometimes that little hand we have another Zoom session, so I'm seeing the scrolling here. I can
No, we seem to be stuck here. I'm not sure.
all right, great.
Now it's working. Yes, we can see that.
All right, sorry about that. Who knows? All right, I'll just go back to my invisible slide. So actually my presentation is quite short, even though it says 15 pages, there's not that number there. So what I was saying was this material here, and I'm up to just mentioning this Jacobi theta function identity. So we're sort of with me, only missed that one page. On to this next page, and I indicate that that particular identity has some implications in the topic that applied topic I was studying, of potentials in ionic crystals, and it gives the electrostatic potential at a specific point. So that's that was my very first mathematical result at the beginning of 1980. During that time, I took interest as well in, as I said, it was the very first time I was introduced to this field of identities, and I took interest in the work of Ramanujan. The work of Ramanujan at the time was being edited by a person called Bruce Berndt. And through some browsing of some of his work, I came across some related identities to Ramanujan that were regarded as worthy enough to get a publication in this Rocky Mountain Journal of Mathematics. So this is like what Jean-Marie quoted from Jacobi yesterday. It's in this mathematical aesthetics, if you like, something a little bit higher here. But indeed, both these left and right hand side can be expressed in terms of Bernoulli numbers, and as Jean-Marie emphasized, the theme of the quote from Jacobi was in number theory. That identity never took off. It doesn't have any physical application, let's say, but what does have physical application, and I was introduced in that time, is the Rogers-Ramanujan identity down here. So let's keep going, not that far behind schedule. So what happened in that same year, I was browsing the physics library and came across this paper of Rodney in Journal of Statistical Physics. And that very much took my attention, although I can't say that I made any study of how this came about, nor did I know anything really about the topic of solving lattice models, interaction around a phase type lattice models that Rodney studied. But I was very interested in the fact that within Australia, we had some mathematical physics people studying identities. Nonetheless, that was not what I tried to. Unlike Murray, I didn't write my own letter to Rodney, even though I may have been tempted. I stayed on at Melbourne and worked on, after ladder sums, this solvable Coulomb systems world. And that was actually turned out to be the topic that I really do, to some extent, still study, mainly through random matrix theory, where the mathematical physics people, Dyson, Gauguin, Mater, were very prominent. And I was supervised by Ed Smith, who'd made some new work involving uses of random matrix theory to the sort of two-dimensional Coulomb system. So it was a sort of a very new topic to some extent, even though the methods of Dyson, etc., go back to the early 1960s. So it turned out to be a topic where there were still many things to do. Right, Ed Smith decided that I should contact Rodney. Well, we heard that Kenneth Lakuta decided that Rodney should go overseas. So good on Ed that he thought I should broaden my exposure to different research topics. And here is the extract from the letter that Rodney wrote back to me after I haven't got the letter that I sent to him, but here we are, 19th of October, 1982. And here's some extracts from this. That first paragraph here, probably a little bit surprising. I've actually brought this up to Rodney sometime later and said, gee, during 1983 and 84, I didn't observe any of this 90% time spent exploring ideas that led nowhere. And he said something like, one sentence reply like, yeah, no, it was a busy time. Nonetheless, perhaps in my letter, I said that I was mostly interested in doing analysis. Well, he said, I know 1% of the time at the very end is analysis. Now, this next paragraph that I've highlighted is one that I believe answers Murray's, well, the point that Murray brought up about Rodney only having the one student. And it was in the early 1980s, as I said, I was the only student, University of Melbourne, you know, population of probably in Melbourne at that time, 3 million people. The only person doing mathematical physics at honours level, joint mathematics and physics. And it was indeed a very depressed time for job chances, if you like. And that's what Rodney was commenting on in the next paragraph. But nonetheless, indeed, it did happen that I became Rodney's student. Okay, let me keep going halfway through the allocated time. I don't want to use up the full allocated time. So 1983, 1984, when I arrived beginning in 1983, very soon after, George Andrews came on an extended visit to ANU, and I think they had already corresponded and had in mind a project called a decorated hard hexagons model. And it had a infinite family of integers labeling these models, and the actual configurations are of the form of solid on solids. Here, this R is the allowed height, so the restricted solid on solid models. Rodney realized during the earlier part of 1983 that this model is actually implied in his work on the 8 vertex model, but only in a sort of a weak sense, in that they have common transfer matrix eigenvalues. What wasn't implied or known from his earlier work was the calculation of the order parameters. And as we saw, or as I mentioned briefly, the famous work of Rodney on the hard hexagon model had encountered the Rogers-Ramanujan identities. So what do you need to know to be able to compute the order parameters? Well, you need to have a copy of either have Rodney as your supervisor or have a copy of his book, or indeed perhaps both. So the story here is in early 1983 at the ANU bookshop, Rodney's book was first available, and I remember very well my weekly salary as a graduate student was 120 Australian dollars a week, and that was $120. But I think that was a very good investment. 1983 of $120 that I got Rodney's book and became Rodney's supervisor. That's a huge understatement. Now, if you turn the book, my copy of Rodney's book on the side, you'll see some dirty finger mark stains that actually are concentrated entirely on one chapter, and the rest, it doesn't look like it's really been flicked through much. And that one chapter is chapter 13 on corner transfer matrices. So that's very much what I was trying to get my head around during that time, when Rodney kindly gave me a few little side problems relating to his project with George. So that project, yes, as I say, I was very fortunate to be part of. Perhaps at the time, the mathematical side of things, of overlaps with Roger's Ramanujan identities, you'd have to think that the market for that amongst the community was relatively small. But as Vladimir told us yesterday, there's incredibly remarkable coincidences going on here. And I should actually, Balaban, Polyakov, and Zemolodchikov, sorry, I missed Zemolodchikov's name there. There was a number of big advances in conformal field theory. And whoops, I spelled David Hughes's name wrong there. But Vladimir correctly spelled David Hughes's name yesterday. And there were these authors that appreciated that this particular model realized an infinite family of the critical exponents as implied by conformal invariance and unitarity. So that became somewhat of a very well-known work that I was extremely fortunate to be part of. And during 1983-84, the other big project of Rodney was the Zemolodchikov model that Vladimir told us a little bit about yesterday. At the time, as we know, later there's some the higher level theoretical significance of the three-dimensional models. But at the time, there was perhaps in statistical mechanics community, the concern was that some of the weights are actually negative. So the interpretation was more challenging from a purely statistical mechanics perspective. Nonetheless, what Rodney was curious about was that the parameterization found by Zamolodchikov involving trigonometric functions coming from spherical geometry, they were trigonometric, and Rodney's experience, and now all our experience in solvable models, is that typically indicates some criticality. So Rodney just thought he could introduce a temperature-like variable and study the model through a numerical procedure. Now, Rodney, as we know, invented the quantum transfer matrices. Underlying the quantum transfer matrices is a variational approach. And what he wrote out some notes for me was a variational approach in the three-dimensional case. But the problem in the three-dimensional case is that the planes in a two-dimensional, or the cutting through the three-dimensional lattice gives something two-dimensional. And the one's basically working with tensors rather than matrices. That's another way of saying it. So actually what was done in that numerical study was using variational equations are actually involving only scalars. Nonetheless, this project worked out. Should thank Tony Gutman in the background there. Tony analyzed the series that Rodney and I had come up with, and we obtained evidence that the Zamolodchikov model was critical. But the big work from Rodney during that period of time, and in fact he wrote this in the letter, I didn't extract that paragraph due to the space, that the Zamolodchikov model that he had proved that the tetrahedron equations were satisfied, the challenge was to compute the free energy. And he did, and that was a project that he was working on and off through that period of time. And he came up with this in the afternoon, just after lunch, July 13th, Friday the 13th, it was, I remember it so well, 1984. And he wrote this out. I put that, you can barely see it, but that's the date, my handwriting at the top, and Rodney's handwriting, where he summarized his findings for the exact free energy in the Zamolodchikov model. So quite an achievement. Last slide, this is it, even though I've got 11 out of 15, not entirely true. So I'd like to say a little bit about what others have said to me, and when the others have said this, I sort of have to say to myself, yeah, it's probably true, because what I'm going to say here is that there is actually something of a Baxter School of Exact Solutions in Statistical Mechanics, at least seen from the other side, and meaning other people. So what do I mean by that? Well, Rodney has indeed great individual achievements on the international stage. And Rodney has given both inspiration and high standing to this solvable and integrable systems studies in Australian mathematical sciences. So Rodney's actual works rather specific within his lattice models, but there's very much, and we've seen this from Vladimir's talk, there is a much broader integrable systems community out there that are very interested in Rodney's work, and that has shone quite a light on Australian mathematical sciences in mathematical physics, and that has some very real consequences. Whereas for a while there, the job market was extremely depressed, yet some of us found jobs, and clearly being associated with Rodney was part of that. And we just find jobs, and then we got some funding, and we were able to then train some other people, and then some of us were in positions where we could have broader influence in the Australian mathematical sciences. So I believe Rodney has this symbolism of a Baxter School. But in my second slide, the one that I was talking at that you couldn't actually see and only flicked over, I did mention the forebearers, and Rodney was already part of that generation that were already in statistical mechanics in Australia, and then since then, many others. And it's really the fact that we do have a critical mass that has made us internationally recognized for the theme, and we think Rodney's been very much a part of that. And what other people have drawn attention to on this theme is that there are centers around the world that one can say similar about. Certainly the Kyoto School has been very important to a number of us in Australia. What might it be called the Leningrad School of It's certainly very prominent, although I don't think Vladimir himself came from the Leningrad School, but nonetheless, there is such an identifiable grouping, and of course at Stony Brook through Yang. On that note, please let me conclude. Thank you.
Thank you very much, Peter. Do we have any questions here in the audience? I just wanted to give you a chance. I'll make a comment. Peter, thanks for sharing that letter from Rodney, actually, about the career prospects.
Yeah, no, sure.
He was, of course, 100% correct. For example, it took me a long time to get a permanent job, and I certainly went down that path, postdoc after postdoc. So he was 100%.
Yep.
It wasn't easy. Yeah. As I said yesterday, I'm still trying to find the letter that he wrote me. Just want to see how it was worded.
Okay. All right. Excellent. Thank you.
Yeah, thank you very much again.